Today we'll continue with the topic on coastal water level fluctuation. We have been looking at the various physical phenomena that causes the water level fluctuation in a coastal area, and the long-term sea level rise is precisely another important aspects that need to be taken into consideration in coastal engineering design. Sea level rise due to climate change can cause the loss of coastal front. It can cause coastal city inundation or flooding. So it's definitely a threat to country like Malaysia with long coastline and many developed area located near the coastal area. Now the changes of sea level can be monitored over the long term using hydrography and land survey, and this has been carried out by DID in cooperation with NAHRIM in Malaysia. This figure shows example of sea level rise that is analyzed from a number of tidal gauge records from 1880 up to year 2000, where for this particular location we can see that over this more than 100 years, the water level has rise by about 20 centimeter. Now we recall that the sea level rise is based on the change in mean sea level, and the mean sea level is analyzed based on the tidal gauge data as we discussed earlier in the topic of tide. These figures here shows the effect of sea level rise. On the left, we see how sea level rise erode the original shoreline, such that after the sea level rise, we have what we call the coastal retreat or shoreline shift. Now, on the right hand side, we have a shoreline which is characterized by rocky features, but still because of the sea level rise, then the part of the shore which is erodible is entirely lost due to the change in water level. In Malaysia, we have introduced the National Coastal Vulnerability Index to identify coastal area exposed to the effect of sea level rise. The study actually covers a number of aspects, including biogeophysical, economic, institutional, and social-cultural factors. The outcome is important for the government in order to identify areas which requires protection so that the necessary budget can be allocated accordingly. The first phase of the study was completed back in year 2007, which covers two pilot sites, Tanjung Piai in Johor and also Pulau Langkawi in Kedah, one in the south and one in the north. So the data obtained from the 20 years of tidal record shows that the rate of the local sea level rise at the two sites are 0.2 to 1.3 mm per year for Tanjung Piai and 0.5 to 1 mm per year for Langkawi, which are actually smaller than the global average. However, we should not take the sea level rise for granted, as the long-term impact can still be noticeable or significant, as we have shown previously, and also we will discuss further in the next slides. Bruns's rule is a simple approximation for us to be able to estimate or calculate the shoreline retreat or beach recession. Here what we see is that, for example, if this is the original profile given by the solid line and the dashed line is the new profile after coastal erosion, and the coastal erosion happens because of the change of water level H, then as wave is able to attack further inshore, then this part of the material is lost to the lower part of the beach profile. So the volume here is lost and form the volume here. The eroded material is deposited up to this point, which is what we call the closure point. So we refer to this as the closure depth. That is the depth and also the location as far as the eroded material can go. This is the dune height at the shoreline, and so this R will be the calculated recession. So R is given by XC, the distance of the closure point, times H, the water level rise, divided by DC plus DD. This is the depth of closure point, and DD is the dune height. Right now, let's look at one example. A beach profile has a closure depth and closure distance of 15 meter and 12 kilometer respectively. Its coastal dune measures average 3 meter high. Estimate the shoreline retreat using Bruns's rule over a period of 100 years if the sea level rise is expected to be 4.3 millimeter per year. So if you apply the equation in the preceding slide, you should be able to get the total sea level rise over the 100 year to be 0.43 meter. And using Bruns's rule, the shoreline retreat will be estimated at close to 300 meter. That's a lot. Even though it's over 100-year time, and you imagine our shoreline is lost by up to 300 meter over the next 100 year. Now this is an arbitrary example, but if we look at here this figure which shows what happened in Hammamet Beach in Tunisia, the shorelines in year 1887 is represented by this white curve, and subsequently the measured shoreline in the later years, and the most recent one is in 2018, which is what we see on the satellite picture represented by the yellow line. So if we look at the scale, the beach here has retreated by up to about a quarter kilometer, that is 250 meter or slightly more, which is about this value. In fact, this 4.3 mm per year is the estimated maximum rate of sea level rise in Tunisia. So this is very close to what actually happened, and it will happen in other parts of the world, and especially along shoreline that is erodable.